Ну вот, можно начинать.
Okay, so I'm going to detail everything that was discussed last time, but in more details and more accurate. So first, I want to start with the definition of Schur processes and Schur measures, and for doing that, I need partitions, which is just a decreasing sequence of integers, and we have a partial order on the space of partitions, which we call interlacing, and this means the following. Also, I think I will need like the length of partition is the number of its positive parts. And also I will need the notation of I don't know what to say, of the size of lambda, which is just sum over all lambda i's. And also we will consider the space of Gibbs von Zetlin, themes, which is just the following. It is the set of interlacing partitions with the condition then that i's partition has no more than has length no more than I, and we will present it graphically in the following way. So this is just the definition of the concept. And also, okay, so this is a definition of Schur polynomial, and for us it will be important that Schur, I'm sorry, I don't know how to control it more. Okay, and for us it will be important that Schur polynomials have interlaced, have the combinatorial, the branching rule, which is the following. And from this, it follows the combinatorial formula for Schur polynomials, which is just the sum over all Gibbs von Zetlin things going to lambda n, all these things. So now we are ready to define Schur measure, and to define Schur measure, we need we need two specializations of we need two specializations of the space of symmetric functions, which I will denote by x and y's. We will try to write like x big and y big. And if we have like x and y, then we can define the following measure on the space of all partitions. And by Cauchy, and here I will use this notation for this thing. And if we have chosen x and y's such that we have this condition for every lambda, and we call such specializations Schur positive specializations, then it is a well-defined measure on the space. It's non-negative, and it sums it sums up to 1 because of the Cauchy identity, that if we sum over all lambdas of this product, then we will get this P of x and y. And also we have defined the Schur process, which is a measure on the space of interlacing arrays, and it also depends on to specializations, Schur positive specializations, and it can be defined as follows, as the following formula. And here I use the notation of Skew Schur functions, Skew Schur function, which in case of one variable is just the following thing. It's written here. So here it's just the indicator function. Also, we have the remark that if we consider level K marginal distribution of such a process, it would be just a Schur measure which has the following specialization. So now I'm going to define first I'm going to define dynamics on the space of Schur processes, and for doing them, I need the stochastic links, which will send this. By GT, I denote just the space of Gelfand settling schemes of size of length n, and this stochastic link goes from this space to this one, if I'm not mistaken. And it is defined as follows. So now I'm going just to define ingredients for building first for building discrete dynamics in the space of Schur processes, and then I will go to its continuous version. So for doing them, I need stochastic links, which can be defined as follows, and these stochastic links can be viewed as a trajectory on a Markov chain with these links being like transition matrices. So this trajectory must go from just empty partition to some fixed partition of size of length no more than n. And it is obvious from the very definition that we have the following formula, because if you look at the formula for Schur processes, if you look at the formula on the right hand side, you can see that all these things will just kill each other, and we will get just the definition of the Schur processes of the Schur process. We will get just these Skew functions on the right hand side. So this formula is just obvious from the very definition, but what it gives to us? It gives to us the following remark, that we can view the distribution of our n parts of our interlacing array system like this, that we start from its highest row, lambda n. We choose it according to the Schur measure, and then we use just some transition links to the previous row. And here I want to say another thing that I will say it before, but for now, if we put, for example, all x's to be equal to 1, then our stochastic link. So what? Wait, I'm sorry. What will we get here? We will get something that will not depend on the path. So if you're thinking about Young graph or something, then this thing is just the probability of some path in the Young graph. And if we put all x's equal to 1, this means that after fixing lambda n, our distribution is just uniform among all the interlacing arrays going from the empty diagram to this chosen diagram. And actually, this specialization, when we put all x's equal to 1, will correspond to our push block process. And this property is called the Gibbs property. Okay, so also, so this was our first ingredient, stochastic links. And another ingredient which we need is Markov operators on the space of the Gelfand-Zetlin teams of the same level, and it is defined as follows. And its main property is that it sends actually this. If you consider like push forward of this Markov operator, then it pushes this measure to this one. And this both these operators, stochastic link and this Markov operator on the space of level n, they are made of some simple Skew functions, and we have a Skew Cauchy identity for Schur polynomials, which I didn't write it at the end, which can be written as follows. Actually, I'm sorry. And this is our main tool for proving, for example, this new. Okay, so here we have two main tools. First tool for dealing with this Schur functions and some operators made of them. The first tool is just combinatorial formula for Schur polynomials, and the second is Skew Cauchy identity. And combining them, we can actually prove the following statement, that actually these two operators, lambda and p, form the commutative diagram of the following way. So here the upper indices just to tell us something about the length of lambda. So here I suppose that the length of lambda is no more than n, and here no more than n minus 1. And we have like the following commutative diagram. And actually, this operators compute in this sense is just equivalent to the Skew Cauchy identity. I will not write the proof, but it is not very difficult. So, and also we have the following properties, that if we have this lambda distributed as this Schur measure, then this one distributed is automatically after push forward of this operator is distributed as follows. This one distributed as follows, and this one distributed as follows. So using
Sveta,
this.
Sveta. And
Yeah.
what is it? P, the map P. What is it? P,
Okay,
K,
yes,
N.
Our operator P here is okay. This thing depends on some parameter on some parameter U, and actually you can see here that that we will have. Okay, so we have parameter U here, and it sends this Schur measure to this one. What is this one? We just, for example, we had the specialization x1, xn, y1, ym. And here we have specialization x1, xn, and y1, ym, and some u at the end. So here, the main property of P is that it sends one Schur measure to another, but with another specialization. And in its specialization, it just adds a parameter U at the end. And it can be seen just from the definition, I suppose. Schur measure and from the combinatorial formula, because in combinatorial formula you have I think I can just go to the beginning. In this combinatorial formula you have this one on the end, and if you add a new variable, you will just have this new multiplicative thing in the Schur polynomial. So U is just an arbitrary complex parameter.
Okay, thank you. And the claim is about Schur measures. So now we don't have any process, yes? Or
yes, for now.
This commutative diagram, it's about Schur measures.
Yes. And now I want to use to build using these computing operators. I want to build a multivariate Markov chain, and it will be now I'm going to define the dynamics on the Schur processes. And okay, so here's just our Markov chain. So what we have here, it's just the previous picture. So here maybe it's better to like, here we have like some indices, and just one thing that is important, that the parameter U is the same here on the horizontal arrows, and there are some ways to build some dynamics on these schemes, but I'm going to choose one of the simplest and the one that will be appropriate for our goals. And so I want now to define the dynamics from this picture, which is called sequential update, and it can be built as follows. First, we will choose so, for example, we're starting from this lambda, and we want to go to this mu. And how to do this? First, I suggest to choose mu1 with respect to the distribution P1. Then I want to choose mu2. How will I do this? So I have this red arrow going from here to here, and I can choose mu2 in some sense like the conditional distribution when we go through this path here and then here, and more precisely we can just write this thing. So actually we will choose mu k with the following probability. So this one is just for going from here to here. This one is just from going from here to here. And this thing is just some normalizing thing. Yes. So.
Sorry, but I don't understand what's written in the denominator.
It's actually the. Yes. It's actually the applying of their composition.
Composition.
Okay. It's actually applying of their composition to this thing. Or we can actually here just to put the sum over all mu we can actually put here just the sum over all mu k, for example, p u of these things, just for normalizing condition. Lambda of new common study. So here.
Okay. Thank you.
Here, yes, and this is what is called like composition of operators, I suppose. If it were matrices, then it could be written as multiplication of matrices. Yes. But yes, maybe from this point, it's more clear why the sum of this probability of the whole, the sum over all mu k minus 1 is equal to 1. So it's actually a good probability measure. But the thing is, in some sense, it is chosen like the conditional distribution of going through this arrow and through this arrow. And also there is another version of equivalent version of how to define this dynamics, is to say that we choose this mu2 independent of lambda 1, and then we choose mu3 independent of lambda 2, and so on. And we constructed just a deterministic algorithm how to go from one state to another one. And as an analog of the previous one, we can say that this the thing pushes. Yes, we know this by PU, and it pushes forward this Schur process to this one. And here we have changed the not the process, just this measure, this measure. Here we have changed lambda to mu as was defined, and also the specialization of Schur process also changed in the same way as before. It's just the new variable added to the y variables. Okay, and so it was like a general construction. And for us, a good case for us will be the following: when we put all x's equal to 1, and first remark I've said before, that we will have like after fixing lambda n, we will have like uniform distributions on the space of interlacing arrows going to lambda n, and then we put all y's equal to each other and equal to t divided by m, and we will consider like m steps, so m level Gibbs settling him, and then we will send m to infinity, and we will have we will have some Schur process with some continuous with the first specialization consisting of just n ones, and the second specialization will be just some continuous specialization, and my claim, it is called Poincaré specialization, and my claim will be that this Schur process will correspond to push block process. So and also we will consider most of the time the initial condition is just zero's initial condition, and okay, so for now it's a little non-convenient, but from now maybe I will return sometimes to the previous axis, but for now we can forget about that, and our axis now will be just the following one. And I want to say that if we will use this correspondence, then lambda will be distributed as I said, then we will just have the push block process. So now a quick reminder, what is a push block process? It is just the following thing. Okay, so we will start with this initial condition, and what do we have? Like each particle, we have like it's a two-dimensional particle system, and each particle has exponential independent exponential clock of rate 1. And what happens if the clock rings? For example, somewhere here. If the clock rings, then our natural dynamics is just to jump to the right by 1. But we have two more rules. First of all is the following, that if we have a particle here then it blocks this one, and it cannot jump. So, for example, this particle, even if the clock rings, this particle can jump to the right. And this is a blocking condition. And if we have a pushing condition, that if some particle jumps to the right, and it has a part. Ну куда все бежало? Извините. Sorry. Okay, so if some particle jumps to the right, and also it is a particle just behind here, then it must push the corresponding particle, and also all the particle just behind this one. So, for example, if this particle, if the clock of this particle rings, then it jumps here, and also this particle jumps here, and also this particle jumps here. And I claim that these conditions preserve interlacing, and actually we will go to the thing that these are just more or less unique conditions that we need to preserve interlacing. And also here there is an illustration how we can graphically think of this. Actually, this process is related to Lozenge tiling of some part of the plane, and the corresponding is just the following. You can see that at each place where we have a particle, we can put this type of Lozenge tiling, and then there is a unique way to draw other Lozenge tiling of this and this type to cover all the area that we can see here. And this interlacing condition is just equivalent to the condition that by such a procedure we can get like a good tiling covering, Lozenge tiling covering. So this is just a visualization. Okay, so and also yes, and also it is shown here that if we look just at the leftmost particles, then we will have a TASEP here, TASEP process here, which has just blocking rule, and if we will follow the rightmost particles, we will have like push ASEP, which is another process, another integrable particle system. And here, if you just look at the top row, we will have also another process. And all this, what good property do we have if we have like this two-dimensional Markov process? That if we have like a Markov process, we can look at this at its marginals, and all the good marginals that we can consider are also some Markov processes, and this is a way to construct them and to do something with them. So okay, and the property that I've actually defined before, but this process actually satisfy the Gibbs property, which means just the following: that if we consider the following conditional distribution, then here I can write anything like some new and some something. I don't know. That if we consider the following condition distribution, then it will depend only on lambda, and moreover, it will be uniform among all the interlacing arrays, so going from the empty diagram to and actually all Gibbs measures obviously form a convex set. And there is a known classification of extreme Gibbs measures, and we can say like that each Gibbs measure can be constructed as maybe not the sum, but maybe sometimes just integral of extreme Gibbs measures. But I don't want to go further in this topic. So the claim is that push block process preserves the class of Gibbs measures, and also and actually I want strictly to prove this theorem, but I can say like more words, maybe more generally, that actually this Gibbs property in the language of Lozenge tiling, this means that in some sense these random tilings are translation invariant, and actually push block process satisfies this condition. So, but I want to say that our process, Schur process that we have built previously, I want to say that it obviously satisfies the Gibbs property. And now I want to say more about so this means that if we will see that the distribution of lambda n behave like the same, then we know the joint distribution of the first n rows. So now I want to develop some analytic machinery for Schur polynomials and so on to prove something for them. So first I want to consider the following bilinear form on this space, and it can be written in two different ways, but for today I will actually need more, not this way. In this way we can see some real integral with some normalized Lebesgue measure on torus, but we can always replace such an integral by a contour integral, and I'm sorry. By this equality, we can always accept of instead of writing this one, use this thing. If we not always, but if you work with holomorphic functions, then everything is good and it can be done. But we will work on this holomorphic function, and also if you will work if we work with holomorphic function, if you work with holomorphic function, then here we don't want to see some conjugation, but we will work with like this thing, and if you like live on the torus, I suppose it is the same. Think of yes, because we can put conjugation to the z variable, and then on the torus conjugation is the same as reverse thing. Okay, so first claim is that Schur polynomials are orthonormal with respect to this bilinear form. And now I'm going to do the sketch of the proof. And this is, we will need this, some of the ideas later. So the proof, there exists like the proof of just considering the first definition of Schur polynomials and writing it's like determinant and determinant and just regrouping and so on. But I want to consider another proof, which is as follows. Consider the following operators. So here some product, and this is just shift operator, and it acts as follows. So this on the function f of it's better to write without indices. It is just the shift operator. It acts just like this. After considering such an operators, we can claim that our Schur polynomials are eigenfunctions for these operators, and their eigenvalues are just the following. It can be done, for example, it can be done actually just by the definition, and also this operator can be considered as like some good conjugation by Vandermonts. So,
you mean we can take determinant representation for Schur polynomials to act on these determinants with such an operator and to see more or less
yes.
by sense? Okay.
Yes. Yes, and this first thing I want to say, this is an operator which has an arbitrary parameter. So it's not like the one operator, but it's an infinitely it's infinitely many operators depending on some arbitrary complex parameter. And for each such operator, we have this property that our Schur functions are just its eigenfunctions with the following eigenvalues.
All of them commute with each other for different Qs. They have the same eigenfunctions. So say independently on Q, they have the same Schur polynomials are eigenfunctions. So all these operators commute with each other. Okay, and they depend on arbitrary complex Q, so we can construct system, integrable system.
Okay, so the thing that these operators also self-adjoint with respect to the bilinear form that I have defined. So we using this, we have our orthogonality and orthonormal condition. Because for example, for orthogonality, if we have like S lambda S mu, we can put this thing, and using that this operator is self-adjoint, we will first, on the one hand, we will have this multiplied by this thing. On the other hand, we will have this room, and we will have, okay, also this, the same thing, but multiplied by this one. So if we have lambda and mu, then we have the following properties, and that this, if they are not orthogonal, then this thing is equal to this one for an arbitrary parameter q, which means that, but it's just some polynomial. So so this means that all lambda I is equal to mu I. So so we have the orthogonality, and also we can really do the similar exercise and to prove that they are really orthonormal. So and using this bilinear form, we can also get integral formula for our Schur polynomials. And how to do this? Our tool for this is the following. For example, we have Cauchy identity. We have Cauchy identity which can be written as follows. And then what I suggest to do? I suggest to multiply both sides, of course, by this thing, and then integrate in the same way as we had like in our definition, and then we will just this integration, because of our orthogonality, will mean this integration means just extracting the coefficient of the corresponding Schur polynomial. So in the left hand side, we should just extract this coefficient, which is as follows. We extract the coefficient of s lambda of x. In this thing, it is just the following. And what do we get? What do we get on the right hand side? By definition, what we have done, we multiplied and we integrate. But as I said, like we do in our definition of our bilinear form, and there we have this thing, and we have this thing we have from the definition, and from our bilinear form we have contour integral, this and this, and for
this the last one is wonderful.
Yes, but it is this thing actually, because we want to deform, to have this ability to deform our contours. So I want to work only with holomorphic functions. And and as I said before, conjugation and reverse is the same on the code. So, but I will, but it's better to use this thing because I want all functions to be holomorphic. And also, this contour integral is, of course, it goes, and it's important. Why it is important? Because we need this contour integral going around 0, but it shouldn't go. It shouldn't contain it should contain poles inside. No poles. So all yj yj to the power of -1 should be outside of our contour, and that is why I want maybe to deform this contour. Actually, we will work with small yj, and they will usually be less than 1, so we don't need like some words, but if needed, then always for now, for the formula to be true, we need no poles except 0 inside our contour. Also, some words needed here about why can we replace, why can we reorder our summation and the integration, but it is just, it's also some technical exercises that can be done. And here, of course, for writing this summation, we need some convergent condition. For example, like this one is okay.
And tell me, please, I have impressions that this multiple integral can be factorized into a product of single integrals.
Which one? The
last one? The last one. No, not this one. The last one you showed. Yes.
But here we have a single integral. No, here we have an
yes. Multiple and both integral.
x1, xn.
Yeah, I guessed, yes. And so this does not so this is very good for factorization. If we just substitute Schur polynomial S lambda as a ratio of determinants, we cancel one of Vandermonts. So we
if
have...
am I right that you're suggesting to use like combinatorial formula for this to write it like
ratio of two determinants? So with Vandermont in denominator.
Okay.
So we cancel one of Vandermonts, we obtain product of two determinants. So such formula is easily factorizable to product of single integrals with respect to each xi. Is it
maybe
useful? No, not maybe. Definitely, I'm sure.
Okay. Yeah.
Maybe,
Yes.
maybe it is useless. I don't know, but I have impression that this integral can be calculated. So,
of course, it can be, because we have like other definitions of our Schur polynomial. We will get
okay. So okay, and yes, and we will come back to S lambda of y.
Yes.
Okay. Yes. Okay. Now I see.
So yes, and why I wanted to write this complicated formula with contour integrals just for Schur polynomial, because these analytic formulas they behave in a good way with some limit taking and so on. And what did we want to do? We wanted to take the following limit, to put all the y's equal to this one and that limit. And using this formula, with the contour integrals, it is very simple because and also we will have like okay, for now I don't need putting x's equal to something. For now, just let's do this transition, and what will we have here? The only thing that depends on y's is just this thing, okay? Even this one, and we know that if we put y is equal to this thing, then we and also we have like the number of y's will equal to m, then we will have just this thing for all x's. But it obviously converges to this, and we can. It's another exercise technical. We can also replace we replace summation and integration, and after that we will no limit with integration, and after that we will have the following formula. Then that our S lambda of I recall that this specialization is just Planck-Range specialization, just the notation for the limiting specialization when we put all y is equal to this one and the numbers m. And here we showed up to some technical details that this limit exists, which wasn't actually obvious at the first time, and we know an exact formula for this specialization from contour integrals. So we have this thing, and here we have our corollary that if we okay, so this is our formula, and our corollary if we put if we now apply our bilinear form again, this thing, then we will get this summation. Yes, and also yes, and also so here it's just I suppose. And also, if you put all x is equal to 1, as we wanted before, then we will get just the following. Then our Schur process will be equal just to the following thing, because what I think maybe it's minus t in the previous.
Probably minus.
Да, там, наверное.
You have minus in the denominator.
Yes. So I need to put minus here and here and here, suppose, and then.
Okay, wait a minute. No. Well, you have minus, but in denominator, so.
Yes. So
you have double minus, which gives plus.
Сейчас. Секундочку. Не нравится. Может быть, там где-то я забыла сопряжение какое-то. Нет. Сейчас. Посмотрим. Посмотрю сюда. Я тоже. Okay, so what? Okay. Yes, it's okay because in the definition of Schur process we should divide by this thing. Actually, it's our. We can denote it like P of. If you remember, okay. So in our definition we had like this thing, or нет, неправильно. Сейчас. So in our definition of the process, we usually divide by the sum over all lambdas. So I think that this minus comes from that we divide by this quantity. So yes. So the thing that if we put all x is equal to 1, then our Schur measure with one variable which is equal to 1 is just indicator function, becomes just an indicator function, and this means that we got just a very simple measure, and it of course it's a joint probability of the interlacing arrays going to the level n, but it is very simple, and it obviously depends just on the lambda n, and here we have just the interlacing condition, and the distribution is just an exponential thing, and this gives us actually Poisson thing, because our Poisson process on just one-dimensional on R can be constructed using uniform measure when we have like when we have our scaling limit regime. So we can just consider uniform measure, and the only thing that we want to preserve is our expectation, which we want to be equal to 1, and then we can push our size to infinity, and we will get just the Poisson distribution. So this is some explanation on why our process is actually the push block process. But I've missed some of steps. Actually, step that I missed, that if you have like this distribution on this lambda n, then actually our rules are exactly a unique way to construct some rules to preserve interlacing condition, and also that the push block process is actually satisfies Gibbs property. But I am hoping that it is believable now that our construction of push block process is actually this Schur process with this specialization. I don't know. Is it clear or not?
Well, yeah, more or less it's clear.
Okay, so it's good. And also we have as a corollary that for TASEP we have the following distribution for this for its dynamics, because we have on the leftmost row we have the dynamics of TASEP. Then and also we know that marginal distribution of Schur process is just Schur measure with the same specialization. So we have the thing. And now I'm going to say something about the asymptotics of this thing and how to get from this an asymptotics of particles in TASEP. So my claim is the following, that both Schur measures and Schur processes are determinantal point processes, which means that its correlation kernel, its correlation functions are just determinants of some fixed correlation kernel of two variables. So this is just the definition of correlation of functions. So first of K correlation function, actually. Maybe it's better to say what is a point process, but it is just a measure which is an intersection of each compact set. We have like a discrete number of points. So it is I think classical. So the claim is that our Schur measure and Schur processes are determinant point processes, and we can write exactly the formula for our correlation kernel. But first, I wanted to say why, how to move from the correlation functions of the Schur measure to the jumps to this distribution in TASEP. So to this distribution, and this can be done using Fried-Golem determinant, because we have actually if our also we have some technique here because we need our correlation kernel to be like trace class operator, and then we can use the technique of Fried-Golem determinant and to get such formula for our distribution of some certain part of our partition. Okay, so the formula for correlation kernel is as follows, and there are different proofs for this. It is the integral formula. Actually, there is another just combinatorial formula using just the there is
generating function.
Yes, there is a yes. I want to say that there is just a combinatorial formula using some generating functions and so on and so forth, and using no analytic stuff at all. And there are different combinatorial proofs and so on. But today I wanted to present a more analytical point, and also, even if you get like a combinatorial formula, you cannot do anything with it. I mean, doing some asymptotics or something in comparison with integral counter-integral formula, because for counter-integrals we have like classical methods of asymptotics, like steepest descent and so on. So here is our formula, and I want to present sketch of proof. And to do this, I wanted I wanted to remind you about our big family of good operators, for which are good in the sense of our Schur polynomials are eigenfunctions of them. And what I want to do first. First, I want to apply these operators to our ordinary Cauchy identity, and we will get something on the left-hand side. We will get something reasonable, and on the right-hand side, we will get something looking like this. But we can actually evaluate the right-hand side using just the evaluating of just looking at the poles of this function and evaluating the residues at these poles and at I suppose maybe at infinity. So after doing that, we will get yes, and also this on the right hand side, this will give us the сейчас я немножко запуталась, конечно. Okay. This will give the expectations. So the thing is that doing this procedure, we can compute our expectation of this value with respect to the measure, to our Schur measure on lambdas. And here we have the formula for arbitrary specializations x and y. But then, as you remember, we want to apply it to our certain specialization where we put x equal to n1s and y equal to rho t, which is our continuous limit. So here actually we have we can get the formula for each specialization, but then for after applying our specialization, I think that okay, that here we have formula for each specialization, and here we have its corollary, because through this thing we can get what is this expectation? It is just this number multiplied by a measure of lambda, and the measure of lambda is just our left-hand side. So this is our expectation. By definition, this is our expectation with respect to our measure, and also, of course, we should get the sum. We should work, and it is just what we get if we apply our operator to the Cauchy identity. So it can be computed through residues, and the answer is just the following. Yes, the following thing, that we have our integration only around these ones, because all the other poles we avoided by computing the residues. They're quite simple. You can just look. They will have like the form, like the following form, because what is the residue? What is the residue at yj to the power of -1. So okay, here we have if we have like this residue, we will have something like this divided by this, and there we will have something that also kills each other. So we will get the following formula, and in our specialization it will give something like that. So by this machinery we will get our expectation for the thing as a contour integral around 1, because all our x's is equal to 1. And then what we want to get from the expectation, we want to get our lambda n, and this maybe this is better to copy and paste, that our probability can be computed actually as follows. So why it is true? Actually, it is true because of the I don't know, just the simple thing that our integral, something strange is written here. I think it should be our but if we have like this thing, then it is just maybe it's better. It's just delta minus 1, maybe like this. And here
why minus 1? I would say 1.
Yes. I'm sorry. Yes. So we have this simple observation, and this allows us to write our probability of n to be included in this thing. Yes, of course, our determinantal process is not just our lambdas, but our lambdas minus lambda y minus y, because our lambdas even don't place like one by another. So we have strict condition only for these things, and they determine the determinantal point process. So we want actually to look at this probability, and by this simple observation, it is just this thing. Okay, and this allows us to compute this expectation using our actually we will need here more, if I'm not mistaken, more our okay, so we can compute these expectations, and then we will have some contour integral formula for this probability. So yes, and another observation will be that this after replacing like integrals with determinants, we will have our determinantal formula. And And the main theorem about this thing is the following one. Then if you consider like the height function of TASEP, then because if you have like integral formula for the correlation kernel, and then we have formula for probability as Friedholm determinant, then we can compute the asymptotics, and I want to formulate the answer. Some of the answers you can get is that if you remember that for TASEP we can always define its height function, which completely determine our process. So it can be built just as follows. We will write this thing for black ones, this thing for white ones, and so on. And asymptotic behavior of this function is just the following: that it is quite intuitive and obvious that it behaves like something linear, but non-obvious part is that it scales like t to the power of 1/3, and the function which we get here is one of two trace-Widom distributions, which can be written as this Friedholm determinant, with our kernel being just an airy kernel. And also this trace-Widom, just a few last words, I suppose, that this trace-Widom distribution has come from random matrices theory, and it is related to the distribution of eigenvalues of random matrix in the Gaussian unitary ensemble. And there are two famous trace-Widom distributions. One is related to the Gaussian unitary ensemble, and another one is related to Gaussian orthogonality ensemble. And if we consider these matrices with respect to this distribution, and we'll look on the eigenvalues of n corner, then we will get just this just the same distribution. So this is what came from. Actually, that's all I wanted to say. Maybe not very detailed, but if you have any questions.
Wow, it's not clear for me what is h of t and tx and what is ci, c1. Sorry.
It's just some functions of x. But the thing that they do not depend on t, and h is the height function. So for example, in our initial condition, we have h of 0, x is equal to this, because we start with this condition.
Okay, yes, now I see.
And so on.